Hello, my name is 𝗬𝗲𝗹𝗵. I'm part of the technical staff here at Vespa. Today I'd like to showcase the Vespa operator, which is our latest enterprise offering, which automates and simplifies much of the processes around running Vespa on Kubernetes. This is essentially our way of making Vespa a first-class citizen of the Kubernetes landscape and trying to encode years of operational excellence and experience that we've gained running Vespa Cloud and running large-scale enterprise, highly available deployments of Vespa, while also maintaining an experience that's familiar to our open source users and ensuring a seamless migration path for those of us that are still on open source. So today, I briefly wanted to go through a technical demo to showcase some of the features and how to install Vespa on Kubernetes, and along the way I'll talk about the various things that the operator can do and also various features and quirks about running Vespa on Kubernetes. Of course, for details, I definitely encourage you to refer to our documentation. So to run Vespa on Kubernetes, our recommended installation path is via the Helm chart. So our Helm chart will create the Vespa operator deployment Kubernetes terms, and it will also install our Vespa custom resource definition, or CRD. So I will briefly open that here. So our Vespa CRD is essentially a way of aggregating all the various components of Vespa into a single definition. And the operator will monitor this resource and ensure that the state in Kubernetes matches the desired state from the CRD. So in the CRD, we can specify various config server and application pod templates, as we say. So these are the ways that we want to configure the config server and the container and the content pods that will run on Kubernetes. Those of you from open source may be familiar with the application package. This is more of an extension of the application package that allows you to specify Kubernetes-native terms, such as, say, sidecars and labels and node affinities and whatnot. So in this little toy example here for the demo, I've specified Vespa with this version over here. So this version corresponds to the Vespa version from open source. And I've also specified that for our config servers, we should use this image here, which I've already pre-uploaded onto our ECR repository that we're using for this demo. There's more instructions on how to do that easily in our documentation. I've also specified a storage type. So Vespa will consume whatever storage type it's given, but we do recommend for the config server using something that's not as latency sensitive, like a remote storage type, such as GP2, which I'm using here. For the application, I'll get into that in a little bit. And I've also, for the config server, told it to place some custom Kubernetes labels. This might be important for your org. So for example, here I've said that the env here is demo, and I've also created just some toy node affinity rules. These are perhaps, say, if you want to schedule the config server pod on a certain Kubernetes node, you could say something like this node affinity over here. And I've also configured a fluent bit sidecar for log aggregation. When it comes to the application, so this application spec, it is an aggregation of the container and content pods, which you might be familiar with from open source. This allows you to specify Kubernetes overrides for your Vespa application pods themselves. We also do provide a way for you to specify this at a more granular level, but this is the easiest way to specify any overrides for the application pods. So in this example, I use the same node affinity and the fluent bit sidecar. It's more of just a demo. For ingress, I've also specified that I don't really want to use ingress here just to make the demo simple, but the Vespa operator also has the option to set up the cloud-specific load balancer for you, if that is something that your org needs. But if you decide to specify your own, or if you want to bring your own ingress, then you could keep the endpoint type as none. All right, so I will move over to installing this. So I'm going to go ahead and use Helm to deploy the Vespa operator. taking just a minute. All right, so I've created a deployment called Vespa operator. Currently, it's just a single pod. So I'll go ahead and just showcase what it's creating. So I created a pod Vespa operator with a suffix. So this Vespa operator will watch for the Vespa resource that I had explained earlier and reconcile towards the state that we had given to it. They show us on the logs what to look out for. So these are healthy logs. We see that the help is set to up. This also corresponds to the Kubernetes readiness probes. So I'm going to go ahead and deploy that Vespa set from before. Right. So now I'm going to just run this flow command to pull the latest state of the pods within this namespace. By the way, the namespace is called demo. So as we can see, there are 2 containers here for each config server pod. One is that little fluid bit sidecar, and then the other one is the config server itself. So when you first deploy Vespa set, that will deploy a config server quorum first. So the config servers will enter a bootstrap sequence, and doing that, it will create a zookeeper quorum. So I'm going to open the logs here. So we can see all the logs for the 3 config servers. By the way, also, there needs to be 3 config servers in order to establish a quorum here. All right, so the bootstrap process has completed. A quorum has been established and consensus has been met. So now I'm going to describe that Vespa custom resource from before. And I just want to showcase the observability that we've also built into the operator. So it shows the spec that I had explained before for our Vespa custom resource. And also, we can see in the status, all of the 3 config server pods are in phase running. And this could be an important signal for you to use to ensure that Bootstrap has completed and we can move on to the next step of deploying the actual Vespa application. Right, so I will move on to deploying the Vespa application. So I'm already inside a directory here for the album recommendation sample app. So users of open source will be familiar with the concept of an application package. So this sample app contains an application package that is pre-built and ready to be deployed. The content of it is not that important. This is more to showcase the actual deployment of an application package. So I will also just showcase real quick what this will create. So this application package has 2 container nodes in the container cluster, which is called default. And the content cluster called music also has 2 nodes. And the resources in the content and container cluster, these will translate directly into Kubernetes pod requests and limits. The operator will automatically do that. So I will open a new tab here. And I'm going to turn on a port forwarding session to the config server. I would encourage to use other ingress types in production, but port forwarding is very simple and easy to demonstrate. So I will set up a port forwarding session to CFG1 in the background, and this is the default config server port 19071. Right. Put this in the background real quick. Okay, so now with the port forwarding session established, I will go to the application package and I will use the Vespa CLI to just copy paste artifact. And this is also a part of the documentation. So I will use the Vespa CLI to deploy this application. Looks like this application has been deployed. And now I want to showcase what the operator is doing here. So I'm going to run that query again to pull for all the pods. So as you can see here, the operator has created the application pods based on the specification that we inputted into the application package. So it has created 2 pods corresponding to the container cluster and 2 pods corresponding to the content cluster. Right. So one more thing. What to also showcase the Vespa set. Oops. Do a describe on that just so we can see the status. So before the status only showed the 3 config server pods, but after deploying the application package, we now have pods for statuses for all of the pods that were part of that specification. It's hoping to showcase how to feed documents to a Vespa and Kubernetes setup and also demonstrate some lifecycle operations during the process. So we have the same setup from before. I'll go ahead and list the pods real quick. So this is the album recommendation sample app with 2 container pods and 2 content pods. So I'm going to show real quick how to feed data. It's the same way that you traditionally would using the Vespa CLI. So like before, you should in production use either the load balancers that the operator provides or your own ingress solution. But for here, I'll use port forwarding just because it's a bit easier to showcase. So I'll port forward the config server port as well as the port to the data plane to the container pod. I just chose one here. Ideally, you would use a load balancer that would forward between the 2 backends. So I've started the port forwarding session. Go back to the edit tab and I'll run a Vespa feed command. I already have a data set as part of this sample app. I'll also do one more just for good measure. So I just fed 2 documents. It's such a small amount that the data will enter a coalescent state nearly immediately. So I'll go ahead and query it, and you see that we have 2 documents. So I just did a quick query here to select all the documents in this schema. So we have 2 documents that aligns with what we expect. And of course, you have the full range of the Vespa CLI to perform various actions on Vespa. So I also want to showcase here a lifecycle operation. So I'm going to delete a pod. I'll delete a content pod. And I want to show that the operator will reconcile the state. So it will create a new content pod in its place, and it will also maintain the data integrity of the system. So I'm going to go ahead and run this command over here. This will delete the pod music103. And the reason why it hangs is because the operator internally has prevented the pod from being fully deleted until the data has been fully migrated over. This is a pretty simple case because we are evicting the pod, so this is a voluntary deletion. The operator can also handle cases such as hardware failure where the deletion is involuntary. And in these cases, the cluster's replication factor will ensure that data integrity is still maintained. So I made the delete request, and now I'll also query the pods, ignore the output on the left. So music103 is being deleted, and the operator created a new pod called music107. So eventually, in about 2 minutes, music103 will be fully deleted, as in the data will have fully migrated over to music 107. And the content cluster will once again be in a coalescent state. And during that time, let's also query the document count just for fun. Yep, so the document count is still 2. And the operator ensures that total coverage, there is no data loss here. It's in about 20 seconds. This should eventually delete music 103. See if that actually works. Yep. So music 103 was deleted. And now we have music 102 and 107. I also want to showcase one more lifecycle operation, which is platform upgrades. So upgrades in Vespa are triggered via the Vespa resource. So in the previous resource, I set the version to 695.32. But to upgrade the Vespa version, all you have to do is simply tick this version up. So in this example, in Vespa set upgraded, I've actually upgraded it to 696.20. And so now if I apply that to the cluster, right? So now that I've applied that to the cluster, let's see. I will list the pods again. So the operator will run an orchestrated upgrade procedure, starting first with the config servers. It will first upgrade all 3 config servers one at a time to ensure that the quorum is still maintained. And then it will upgrade all application pods in parallel. So the cluster controller, the container cluster, and the content cluster each will start their own upgrade procedure. And eventually, after about 20 minutes, the cluster will have been fully upgraded. The operator ensures that there's no loss of coverage, no degraded performance, and no data loss during this procedure.